thanks for the introduction, Christina, and thanks to the organizers for the invitation to speak here today. So yeah, I'm going to talk about some of the work I did at UCL as a postdoc on using deep neural networks for analyzing NMR data and some of the cool things we think you can do with them. It's slightly intimidating to follow Ilya's talk, but I'll be kind of reiterating some of the things he said, but also we take a slightly different slant, and hopefully some of the applications we show will be exciting. So I'd like to acknowledge these people. So this is all work done in Fleming Hansen's lab at UCL. So unfortunately, I'm no longer there, but it's fun to be at the conference and learn about the cool things happening in the bio-NMR community. So a huge thanks to Fleming for kind of supervising the project and coming up with loads of great ideas all the time. And then Harry and Vaibhav were involved in a lot of the work, especially collecting a lot of the data we used for validation, and then the other members of the group for good chats and coffees. And this is the group in kind of pandemic times. Okay. So Ilya's already touched on some of this stuff, but how we kind of see some of these things. So very broadly speaking, deep learning is a kind of machine learning where we use these things called deep neural networks, which are kind of loosely inspired by the structure of animal brains to try and perform functions. So the basic type of neural network looks something like this. So you would call this a multi-layer perceptron model. And basically it consists of an input layer. So you have some input, then you have these hidden layers, and then it gives you out some output. So the key thing about a deep neural network is you give it an input, or at least in supervised learning, and I'll come back to that, and you give it an output, and then it works out for itself how to map between these two things. So through a process called training, these hidden layers work out how best to get from the input to the output. And I think this has been mentioned already in this session. So the reason we get excited by deep neural networks is because of papers like this, so AlphaFold has kind of solved the protein structure prediction problem to some extent, or certainly outperforms anything else by a significant margin that came before it. And so I think there's clear potential for us to use it more in the kind of magnetic resonance community. And I think we're going to be seeing a lot more of it going forward. And today I want to talk about our small kind of contribution to that. So the kind of deep learning we're doing is supervised deep learning. And what that means is you have an input and an output, and Ilya kind of touched on this. So you want to map the input to the output through this training process, and you give the network annotated training data. And we have this massive advantage in NMR and in EPR, I guess, as well, that we are well aware of how experimental data looks. And so we can create arbitrary amounts of labeled training data. And then it's just a case of kind of crunching this through the network and to try and work out solutions to problems. So then when we supply it with unknown data, it can kind of do these same kinds of transformations. So just a brief survey of some of the things people have done before in NMR. So automated peak picking, which has been discussed already. I'm not saying any of these things are better than other algorithms. They're just kind of things that people have worked on. So chemical shift prediction, spectral denoising, virtual decoupling, and reconstructing non-uniformly sampled spectra. So what I'm going to talk about today is going to be these things I've circled. So reconstructing non-uniform sampled spectra firstly, and then some stuff on virtual decoupling, and I'll touch a little bit on spectral denoising as well. And one thing, so I want to particularly highlight is how in light of having kind of deep neural networks, you can really rethink the kinds of experiments you're doing. And I think there's a lot of scope for doing exciting things in that space. So it's not just about, can we do things better than we could before by using a deep neural network? A question you can really begin to ask, and hopefully I can convince you of this through this talk, is, well, can we now rethink the experiment we're doing now that we have this cool thing to kind of process or transform the data to give us better results? So I'm going to start with our architecture. So we call it FIDNet. And the reason we call it FIDNet is because the architecture works with time domain NMR data. And this was a kind of a decision we made early on. And so we're used to seeing NMR spectra in the frequency domain after they've been Fourier transformed. But our network runs in the time domain. And the main reason for that is basically that when you go from the process of going from the time domain to the frequency domain, there's equivalently good information. The Fourier transform is a linear transformation, but the good thing about working the time domain is it's closer to what comes out of the spectrometer, basically. So normally when you convert things to frequency domain, you often apply things like window functions and zero filling. You might do linear prediction and lots of other things, and they can come in different forms. And so that means if you want to expose that to your neural network, you then have to cover all of those possibilities in your training data. If instead we work with time domain data, we can kind of avoid that problem, hopefully, and just work directly with stuff that's as close to coming off the spectrometer as possible. And then once we've made the transformations we want to, the user can then go and apply whatever window functions and zero filling, etc., that they want to, and we don't really have to be too concerned about that in the training process. So that's why we work in the time domain. But the kind of disadvantage of doing that is, let's go back, that unlike the frequency domain where information is really localized to a specific point in frequency space, like information in the time domain is spread out through the whole thing. So your resonance frequency is defined by the frequency you see through the whole FID. You can't just look at a point or a few points and say with much accuracy what a frequency is. Similarly, your relaxation, so your line width, is defined by how the thing decays over the length of the FID that you've measured. So if you want to extract information from an FID, unlike the frequency domain where things are very localized, you need a way of looking and recognizing both long and short-term patterns. And a lot of work that's gone into kind of deep neural networks to date, especially in kind of image recognition, is all about recognizing kind of localized things and spatial things that are close to each other. And so this presents a slightly different challenge. But to address this, one thing I noticed early on was, well, FIDs kind of look a bit like audio signals. And quite a few years ago now, DeepMind and Google developed this deep neural network architecture called WaveNet, which was used as a model for generating audio. So you would give it something and then it would like say what the next kind of notes would be or whatever. So this was to generate new audio, and now they use this in lots of their technologies. And if you're looking at audio, you have this similar problem where you can't just look at the last few things. You want to understand the long range patterns in the signal as well. And the way they addressed this was by using these dilated convolutional layers. So the networks we use are not fully connected as they are in DeerNet, but they use these things called convolutional layers, which are effectively filters that slide over your image or your signal or your audio or whatever it may be, and produce an output. So what the network does is learns what what these filters should be to produce a desired output. And the trick that we use here effectively to look at both long and short-term patterns within our signal is to introduce these dilations. So this is the key to WaveNet. So you can look at short-term patterns in the data by having no dilations, but you can have what is effectively the same sized filter, but with these dilations introduced, so these holes, to get access to long range patterns as well in the data. And by stacking these things on top of each other, basically, you can get a handle on both what's happening at short times as well as long times. And then the network has a few more complications in it, which are mainly there to basically speed up convergence. So I need to hold my hands up here and say, we don't have a particularly good handle on how this network performs the transformations it does. And, I think that's relatively endemic in the field. And I think Ilya's group is one of the few who've had have shown like really how these things can be cracked open and work. But this is an extremely large network. So we're talking about millions of parameters here with hundreds of filters. And there's almost certainly some redundancy in there, but working out what is and isn't redundant is not straightforward, because these take on the orders, well, these networks this large take on the orders of kind of weeks to train, at least with the GPUs we have access to. And so we've kind of taken a more empirical approach and seen that this seems to work reasonably well. We can kind of speculate on why, and we think these dilated convolutional layers certainly help convergence and help things train faster. I have no doubt that you could do this with a fully connected network, provided it was big enough, but I think the training would probably be a bit more challenging. But yeah, I'm happy to answer more questions about the network architecture going forward. But now I want to kind of show the kinds of things that we put this to work to do. So the first problem we wanted to tackle was non-uniformly sampling, reconstructing non-uniformly sampled data, which is something that Fleming had worked on before I turned up. And it worked well, except that it lacked any kind of flexibility. So the first challenge was, well, how can we take this from being something that works well in a very small number of cases to maybe work slightly less well, but can be applied in kind of any case. So normally when you do NMR or 2D NMR or 3D or 4D, well, in 2D NMR, you would usually get a fully sampled spectrum. And in 3D also, you'd usually get a fully sampled spectrum. And that means you collect every number, all of your points in the indirect dimensions. And if you Fourier transform the direct dimension and leave the indirect dimension as is, you get this kind of interferogram, which you then Fourier transform again, and you get a nice spectrum. In non-uniform sampling, what you say is, well, it takes me quite a long time to record all of those indirect points. Like each indirect point means you're collecting another two 1D spectra effectively. So why don't I just collect some of them, and then you'll get an interferogram that looks like this. The issue is you then, if you Fourier transform that, you get a mess. So what you need is some kind of algorithm, be it a deep neural network or something else, that can reconstruct your missing points so that when you do your final Fourier transform, you get back to something sensible. So there's a few things you need to take care of when you're going to do a NUS experiment, namely the sampling rate and the sampling schedule. So if you have a fully sampled spectra that looks like the FI, or fully sampled FID, that looks like the thing on the left, and then a non-uniformly sampled thing where the points that aren't sampled have just been replaced with zeros for clarity. The things you have to think about are the sampling rate. So what percentage of the total number of points do I want am I actually going to record? And there's a trade-off here, which is if you have a lower sampling rate, you will get your spectrum more quickly. But on the other hand, you're asking your reconstruction algorithm to do more work. You might, if you go too low, you might get yourself into a situation where it's mathematically impossible to reconstruct the spectrum because you don't have enough points for the number of signals you have. And then the other thing to consider is the sampling schedule. So that is, okay, so I have this sampling rate, but which points am I going to leave out? Or which points am I going to record? And you have various choices here. You could just choose randomly, which is a slightly risky choice, especially at low sampling rates. Or you could say, I'm going to go for Poisson gap sampling, which means I'm going to have kind of regularly spaced points that I'm going to sample with some randomness in there. You could also add some weighting to your Poisson sampling. So you're more likely to get early time points where things are a bit more intense and you have these decisions to make. So what we did when we trained FIDNet to do this was the aim was to make it as flexible as possible. So we trained it with completely random sampling schedules. So as the data went through the kind of training pipeline, it was just a random sampling schedule would be made on the fly, and that kind of mask was applied to the data, and then it was asked to reconstruct. So we think that gives it some of its flexibility. And also something worth noting is that, so there are a lot of good existing algorithms for reconstructing non-uniformly sampled data. So, and when you get to kind of higher sampling rates, their performance is very similar. So the real question we want to ask is, can we get to, how do we do at very low sampling rates where other things might struggle a little bit? And so here are some results. Oh, okay. Before I get to results, this is how FIDNet works in practice, which is it splits up the spectrum into little sections, batches them together, puts them through the deep neural network in parallel, and then stitches the spectrum back together. So to do this quickly, you need a GPU. It doesn't need to be a very fancy GPU. We trained this on an NVIDIA, or we ran this on an NVIDIA 1070, and which will cost you a few £100, I think. And a typical 2D spectrum can be reconstructed in a few seconds. You can run this on NMR box, which has a few GPUs, and you'll see similar kinds of times. If you try to run this on a CPU, it can be run, but you're talking about it taking minutes rather than seconds. Okay, so here are some results and some comparisons with what other algorithms can do. So this is the SH3 domain of ABP1P. So here we're looking at very low sampling rates, so 12.5%. So in pink is the fully sampled spectrum, so collecting all 120 points, and then from that we've taken out 87.5% of the points and tried each of the algorithms on it. And on the right, you'll see the RMSDs. So a lower RMSD means a better reconstruction, and those are the average of 100 reconstructions. And then an example is shown on the panel on the left. So for this protein, you can see with SMILE, you get quite a few streaky artifacts. IST, HMS IST does a pretty good job at reconstructing this, as does FIDNet. One difference you can see between the two is that if you look at the RMSD, is that HMS IST is very reliant on having, or more reliant on having, a Poisson gap sampling schedule to reach optimum performance. Poisson gap is also better for FIDNet, but it matters to a lesser extent. So you can outperform HMS IST when you use random sampling, and SMILE doesn't really care about the sampling schedule, at least in this case, but performs significantly worse. Another example, which is a bit more challenging, you have a few more peaks, is T4 lysozyme. in this case, FIDNet is slightly worse than the other two, at least with, well, it's similar to SMILE with Poisson sampling, and worse than SMILE with random sampling, and better than HMS-IST with random sampling. But you can, if you look at the spectra visually, you can't see any big differences, but you'll notice there's a couple of peaks missing. And then the performance is broadly similar between the three programs. If you look at the y-axis, the numbers are all low across the board. And then this is quite a challenging case. So this is a methyl-TROSY spectrum of HDAC8, which is a protein we look at quite a lot in the lab. So reconstructed from, again, 12.5% sampling. And you can see FIDNet is doing a pretty good job. And you certainly get less. So in general, what we see with FIDNet is you tend to get less false positives. It's a bit less good at accurately, when I say accurately, getting the frequency and intensity of peaks bang on. But in general, you tend to get less false positives than you do with other things. And if you look at the paper, which was published in JBNMR at the start of this year, we try and have a thorough go at identifying where we do better and where we do worse than existing programs. But at the moment, I think this is a viable alternative. It does a decent job. It's not clearly better, but it's certainly in the same ballpark as kind of best in class at the moment. And one other thing you can get, so because, let me show you this again, because we have this, so we run this algorithm effectively as a sliding window. So what that means is that each point is actually reconstructed multiple times. And so for the final spectrum we show, we just take the average of those. But to get some insight into uncertainty, because we're not really in a position where we can train an ensemble of these in a reasonable time frame, what we can do is look at the uncertainty between repeated reconstructions, where the window over which the reconstruction is taking place is altered slightly. And this can help us identify either where we have false positives or where intensities are likely to be a bit messed up. So here's an example for ABP1P and HDAC8 at the bottom around 30 ppm in carbon and 0.7 ppm here. That can identify a false positive in the reconstruction, which is quite a nice feature, but it's certainly not something you can use quantitatively, but it's a useful, I think, qualitative guide to how your reconstruction has gone. Okay, so having done that, the initial plan was, well, this is quite nice. Why don't we try and do 3Ds and 4Ds? But then when I got talking to Fleming, I think what we decided was, well, this is all well and good, but we're not clearly doing better than what's out there already. So what we felt we should do is turn our attention to problems where there are no good solutions at the moment, or where we can quite easily beat what's already out there. And I think that's where some of our most exciting results are. So the first thing we thought about was virtual decoupling. So this is important in especially in 13C detect experiments, which we're doing a lot of in the lab now. So often you have a homonuclear coupling that evolves during acquisition, and sometimes you can get rid of that experimentally using a technique like low BAST, where you pulse during detection, but that's not always feasible and is sometimes not viable. So usually what you do is something like an IPAP, where you record two spectra, an in-phase and anti-phase, and then you take linear combinations to get your final spectrum. But we thought, well, can we make things a bit easier by just taking, say, an in-phase spectrum, applying a deep neural network and getting a decoupled spectrum out, and then we've kind of halved the minimum phase cycle, effective minimum phase cycle of the experiment. And so we first applied this to CC correlation spectra, which is something, so these were used to look at side chains of proteins. So you'd run this experiment on a uniformly deuterated protein. And this is something that was developed by Ruth when she was in Fleming's lab. And so you can get nice spectra of protein side chains where you have a terminal carbon and a penultimate carbon with slightly different chemical shift distributions. And usually you would resolve the homonuclear coupling by doing an IPAP. But we've been able to train the deep neural network to do this on purely the in-phase spectrum, so halving the amount of time the experiment takes, and we get similar results to IPAP in half the time. So we just take in the in-phase, we run the deep neural network and get nice spectra out, whereas the IPAP would also require the anti-phase component and then taking linear combinations. You'll notice here that the deep neural network is trained to try and denoise the spectrum as well, which is why you can get these very clean baselines at the end. And so the beauty of this is that the deep neural network doesn't care about what residue you've chosen to look at. As long as the coupling is the right size, it's trained to decouple it. So you can also do this on isoleucines, but you could do it on any residue where you have this same kind of coupling. So you could argue the CC correlation spectra are kind of easy because you don't actually have that many peaks. There's not too much overlap. So for a more challenging case, we move to con spectra. And these correlate amide resonances with the preceding carbonyl and are particularly useful for studying IDPs at physiological temperatures and pHs where solvent exchange can kind of blur out your signal. So here's a con spectra of ubiquitin. So in this case, we can decouple these really well, again, show similar results to IPAP in half the time, get nice clean decoupling, and many NMR spectroscopists favor IDP alpha synuclein. We get similarly nice results, even where we have significant overlap between peaks. And it's really just a case of popping it in and getting out a nice decoupled spectrum. And we can also run this experiment on HNCA and HNCOCA spectra. So in this case, you have an extra complication. So often resolution is limited by this 35 Hertz coupling between C alpha and C beta. And you can try some like band selective inversion approaches to get rid of this, but they're always a bit of a struggle because you have serines and threonines where the C alpha and C betas overlap. And then you also, if you're going to use other like methods for deconvolution to decouple, you have to figure out strategies to deal with the glycines where you have no coupling. With the deep neural network, we can just pop this into the network, make it aware of the fact that it may come across a glycine where there is no coupling. And so it will just leave that alone and nicely decouple everything else and give us a much better resolved spectrum, which is nice. So far I've shown you cases where you have a single homonuclear coupling. And I think the FIDNet approach is quite nice in that it's flexible. It can reduce the effective phase cycle. You could argue that in many cases you could use like a low bash approach, which would give you similar results, which is true, but FIDNet can do this in cases where low bash wouldn't work, for example, with the side chain correlation experiments. But can we take this even further? And the answer is we can. And this is where I want to come back to this idea of how can we combine our experiment and our analysis mode. So if we think about C alpha acquire experiments, these are a bit more challenging because it's no longer, if you want to decouple these fully, you have two couplings to deal with now. You have a CO coupling, which is about 55 Hertz, and then a C beta coupling, which is about 35 Hertz. And then you also have this issue that glycines don't have the C beta. And if you wanted to do band selective decoupling, you have this issue with like serines and threonines again. So normally the best you could do is to do like a DIPAP or a double spin state selective excitation type scheme to resolve this. But that then requires getting 4 spectra instead of 2 and taking linear combinations. And even then, it's not that great. So this is a DIPAP decoupled spectrum of ubiquitin. And you can see that it's kind of messy. Most things are decoupled, but your glycines are a bit of a mess. And yeah, it's not great. And that's with a very long experiment. So how can we do better? So we could have taken a similar approach and tried to get an in-phase spectrum and then try to train a neural network to deal with that. But we try to be a little bit more creative and look, and we like doing playing with spins on the spectrometer. And so we looked for pulse sequences. And so we have this kind of pulse sequence for recording a COCA experiment. And at the end, you have this DIPAP block. And that's to create your various in-phase, anti-phase combinations, which you need to take linear combinations of to get your final spectrum. And we thought, well, why don't we just get rid of that? And this is a pulse sequence that already exists on Bruker spectrometers. And what this would give you, so you have a semi-constant time portion where you're recording chemical shift of CO, and then you bring that up, you bring your C alpha down, and you start recording. So what you end up with is a shorter sequence, but it also gives you much cleaner data. So what you end up with is a spectrum which is anti-phase with respect to the CO and in phase with respect to the C alpha. And you get a nice clean spectrum, which has also got higher signal to noise because the sequence is shorter. And now we have something nice to give to our deep neural network to try and decouple, which is what we did. So on the left, there is the input to the deep neural network. Then we decouple that to give us the nice spectra in the middle. So that's a nice C alpha CO spectrum, purely on the basis of that spectrum to its left. And then we have a DIPAP decoupled spectrum. The spectrum on the right took twice as long to record, actually, and clearly is worse than the FIDNet decoupled thing on the basis of the anti-phase in-phase spectrum alone. And here on the right is another example with T4 lysozyme. We didn't run the DIPAP on that because it would take too long. But so this is something that excites us a lot, this idea that you can rethink the experiment you're doing to suit the analysis mode, and you can come up with better results. And then we wanted to take this one step further. So this is a slight change of tack. So I think everyone in this audience will know you have kind of an issue with size in biomolecular NMR, and a lot of work has been put into overcoming that. And so typically what you do if you wanted to look at something, on the order of hundreds of kilodaltons, is to use specific methyl labeling against a deuterated background. And you can get beautiful spectra doing this. There are lots of experimental methods based on this technique now, but it requires you to grow your sample in D2O, add these specific labels. Not everything will grow in D2O. It's kind of expensive, but it's the best we can do at the moment, and it is very good. But one thing we realized was that methyl groups are kind of intrinsically intense. So if we look at spectra in the methyl region of increasingly large proteins, although things get a bit messy, and obviously you get broad line widths and you get more peaks as things get bigger, what you still have is quite a lot of signal. So these are all HSQC spectra recorded maybe an hour, not more than that. And even for MSG, which would be considered very large, so this is uniformly carbon labeled and protonated, not deuterated, you still have quite a lot of signal there. The issue is not really the sensitivity, it's the resolution. So you can't really see what's going on to the naked eye, but certainly it's clear that there is signal there. So what we thought was, well, we've been playing with these FIDs. If we consider the FID in such a system, well, there's kind of two things to overcome. A, we have this coupling to terminal carbons in methyl groups, which halves peak heights and limits resolution. And then also resolution is intrinsically limited by the can we train a network to overcome both of these things at the same time? So A, to decouple, and B, to make the signal persist for longer and give us sharper peaks. And I'll skip to the end and say, basically, yes, we can. So at the top there that's a spectrum in blue of MSG. So that's a deuterated ILV labeled sample. And below that is just a uniformly carbon labeled protonated sample of MSG. So that's significantly cheaper to make and will typically give you higher yields and less stress for the poor soul who has to make it. And you can get really nice spectra. Once you put it through the deep neural network, for free, you'll get resonances associated with all methyl groups. So that's isoleucine, leucine, valine, methionine, alanine, threonine. You'll get isoleucine delta 1 as well as gamma 2. So you get more probes for free, which may be an advantage or a disadvantage depending on how you see it, but they're all there. And you don't, whereas if you wanted to do this with the kind of traditional scheme, you'd have to introduce those specific kind of reagents to make that happen. And if we start comparing this to ILV style spectra, you can see you can make it such that you get similar kinds of line widths. So now you can take this data, which is there. So this is the point I want to make. This isn't introducing anything that isn't there anyway. It's just a way of making this information accessible to an end user. So you can see the signal is there in the original spectra, but now it's with the line widths you'd expect of an ILV style spectrum. And so you can interpret it essentially. Yeah, and obviously where there are peaks, you can see they overlap well with the ILV spectrum, and you obviously get some additional ones. So yeah, this is something we're working on at the moment that we're quite excited about. So yeah, that's it. So yeah, to summarize, deep learning is a super flexible technique at our disposal now, and is really well disposed to problems in NMR, I think, because of this thing that we've talked about, having the ability to get arbitrary amounts of training data quickly. So the applications I've shown you are reconstructing non-uniformly sampled data, virtual decoupling, and sharpening spectra. And yeah, so this is the thing. So I think it opens up experimental possibilities which seemed a bit daft otherwise, like, oh, let's run a 2D spectrum of uniformly labeled protonated MSG in an hour and see what happens. Well, you can actually get some quite decent data if you use some of these techniques. And yeah, so if you want to get in contact, all the code is on GitHub. There's my email address, which still works and still should work for the next 2 years, or you can contact me on Twitter. Thank you.